factor each completely. This is a type of problem that we call, or a type of expression rather, that we call a difference of squares, and we'll see why in just a second. But what we're going to learn how to do is factor that, and factor means to take one expression and turn it into a multiplication problem, where you have one thing times another thing gives you your original expression. So let's get the prime factorization of m squared. That is, I want to know all the prime, or as close as I can get to prime numbers, that when multiplied together give me n squared. And the best I can say is m times m. And then I'm going to look at the same thing for 9. And when I get the prime factorization of 9, I get that it's 3 times 3. So what I see here is that m squared is a perfect square. It's m times m. And 9 is a perfect square. It's 3 times 3. So when I see this situation, that this is a perfect square and this is a perfect square, there's a certain form that our factored form is going to take that's very easy to remember. So when we get our factored form, it's going to look like a binomial times a binomial. And the way we write this out is that we take the square root of this first term, which would be m. It's just one of those terms that you're multiplying together. And that's going to be the first term in both binomials. Then I take the square root of the second one. So that would be 3. So the square root of 9 would be 3. And that's going to be my ending number in both polynomials. And what I do is I say I'm going to add one and subtract the other. And now if I multiply these together, something pretty neat happens. M times m is m squared. M times negative 3 would be negative 3m. 3 times m would be positive 3m. That negative 3m and positive 3m will cancel each other out. And so the only thing I'm left with would be m squared minus 9. So this is going to be the form of anything you factor that is a difference of two squares. Remember, difference means subtraction, and that's hugely important. If this is a plus sign in between it, this does not work. This technique only works when you have the difference, when you're subtracting two perfect squares. So let's look at 16. We have to determine if these are perfect squares or not, and the way we do this is we look at 25 and we determine, is there any number times itself that gives us 25? Sure there is. 5. 5 times 5 is 25. So 25n squared is just 5n times 5n. So it's a perfect square. 16 is a perfect square as well. Notice I'm not taking this all the way down to prime factorization, but I am noticing that 16 is 4 times 4. So I can write my factors for this, my two binomials, by taking the square root of the first one. So that's just one of these terms, 5n and 5n. And then for the second terms, it's just going to be the square root of 16, which is 4. Add 1, subtract the other, and this is now factored.